Ever find yourself, totally geeking out about quantum computers, like how they could, like, totally change how we look at quantum field theories?
Oh, absolutely. We're talking about like the fundamental laws of physics here, right?
Right. And this paper, it's all about tackling that. Simulating something as crazy complex as a quantum field theory. Even with quantum computers, it's a huge challenge. But that's where this whole Hamiltonian truncation thing comes in, right?
Yeah, it's
It's
why.
like, imagine trying to cram this massive, super complex simulation onto a computer chip. It doesn't fit. Hamiltonian truncation, it's like shrinking that simulation down, making it manageable without like losing the important stuff.
Exactly. It's this really smart strategic simplification. We zero in on the most important parts of the system's energy. That's all controlled by something we call a Hamiltonian.
Hmm.
And the less important parts, we toss them aside. Makes the calculations way easier to handle.
So we're simplifying, but how do we even know if this like shrunk down simulation is even accurate?
That's where our good friend, the Schwinger model, comes in. Think of it like a quantum playground, right? It's a simpler kind of QFT that lets us test out these new methods, like a testing ground for Hamiltonian truncation.
Okay, I like that. A quantum playground. But why this specific playground? What makes it so special?
Well, in its most basic form, it's what we call exactly solvable. Like we already know the exact answer. So we can test out Hamiltonian truncation on it and immediately see how its accuracy stacks up against the more, I guess you could say, traditional techniques. But here's the cool part. It's still complex enough that we can see some of these really interesting phenomena that pop up in way more complicated theories. Things like quantum chromodynamics, QCD.
Whoa! Okay, so back up a sec. QCD.
Yeah, so QCD, that's the theory that explains how quarks and gluons interact. The stuff that makes up protons and neutrons.
Right, got it. Okay, so the Schwinger model, it's like this perfect balance. Complex enough to be relevant to the big stuff, but simple enough that we can actually wrap our heads around it, see if we're messing things up.
Exactly.
So, like, how do we actually use Hamiltonian truncation in this quantum playground? What does that even look like?
Okay, picture this. You've got this system, right? And we carefully set it up in its lowest energy state. We call it the ground state. It's like winding up a spring, storing all this potential energy.
Yeah, I'm with you. Winding the spring.
Then, bam,
Mm.
we introduce a new interaction, like suddenly switching on a new force or adding a new particle into the mix. It's like we're giving the system this sudden jolt. Physicists have a fun name for this, a quench.
A quench. So we're basically like shaking things up and seeing how the system reacts to being thrown off balance.
Precisely. And by watching how it evolves after the quench, how the energy redistributes, for example, we can start to understand the fundamental dynamics of the system. This this is where Hamiltonian truncation really flexes its muscles.
So did it bulk up? Did it work? What kind of results did they get?
All right, so buckle up because the results are pretty impressive. Remember, we're working with these NISQ devices, today's quantum computers. And they're still kind of, well, finicky.
Finicky how?
They've got limited processing power, limited qubits, and their coherence times, how long they can hold on to information before it kind of degrades, it's still pretty short.
Okay, so limited tools. Got it. What were they able to do with that?
Here's the mind-blowing part. They pulled off accurate simulations of this Schwinger model after the quench. And get this, they did it with a tiny number of qubits.
How tiny are we talking?
Try 2.
2 qubits.
Yeah.
Seriously, how is that even possible?
It's a testament to how powerful Hamiltonian truncation can be. To do that with such limited resources, that's huge. It opens up all these possibilities for what we can achieve, even with the technology we have right now.
This is where it gets really interesting, right? They didn't just stop at simulations.
Oh no, they went a step further. They wanted to see if this would work out in the real world, not just on paper. So they took their simulation and ran it on an actual NISQ device, not some idealized, perfect quantum computer. The real deal.
They put it all on the line. So what happened?
The results, they lined up incredibly well, like scarily close to the more resource-intensive simulations, even with all the noise and imperfections you get from a real-world NISQ device.
This wasn't just a thought experiment. It actually worked. It really makes you wonder what's next.
It's like opening this door to a whole new world of exploration, Even with the limitations we have right now, the possibilities, they're incredible.
Okay, so we've set the stage here, but I need more. This is huge, but where does it go from here? What's the next chapter for Hamiltonian truncation?
Well, it's like you've discovered this new path, right? Now you want to see where it leads. And that's where things get really interesting. And you know what's really cool? This isn't just theoretical anymore. It's like we've had this door right there in front of us. This idea of using NISQ devices to really make headway with QFT simulations and this research. It's like finding the key, unlocking that door.
We've talked about those NISQ devices a bit, and yeah, they're still in their early stages, but are you saying we can start using them now? Like today, to tackle a problem we thought were years away.
That's exactly it. We've figured out this way to use the tools we have right now just by being smart about it, thinking outside the box.
Okay, I'm picking up what you're putting down. But this is huge for quantum physics, sure, but
Yeah.
for someone like me, someone listening who maybe isn't a physicist, what's the big takeaway here? What does simulating these QFTs actually change?
That is the million-dollar question, and it always gets me pumped. Just imagine a world where we understand how matter behaves at the quantum level so well, so precisely, that we can build totally new materials. Stuff we haven't even dreamed of.
Like what? Give me an example.
Okay. How about superconductors that work at room temperature? No more needing crazy, expensive, energy-sucking cooling systems.
Yeah.
That's not sci-fi anymore. That's within our grasp.
Okay, I see where you're going with this. More efficient power grids, faster computers, stuff that affects everyone every day.
You got it. And that's just scratching the surface. Think about medicine. If we can simulate how molecules and drugs actually interact at the most basic level, we're talking designing better treatments, fewer side effects, the works. We're talking about using quantum mechanics to solve some of the biggest problems we face as a species.
Okay, whoa, that's a lot to take in. A revolution in how we approach everything from energy to medicine. My brain's kind of fried.
Uh-huh. Yeah, it's exciting stuff. But you got to remember, we're still in the early days. We've got a lot of work ahead of us, both with the hardware, those quantum computers, and the software, how we program them, before we see the full potential of all this.
So this research is like baby steps for quantum computers, maybe, but a giant leap for our understanding of the universe kind of thing.
I like that. That's a good way to put it. It's a marathon, not a sprint, right?
Okay.
But it's research like this that shows us we're on the right track. We're pushing those boundaries of what's possible.
And hopefully making life better for everyone along the way. This is really groundbreaking stuff. And speaking of groundbreaking, this research makes you think about the universe, our place in it all, in a whole new way.
It really does. It makes you realize how much we still don't know. There's so much out there waiting to be discovered.
It really makes you think, right? I mean, we're talking about using quantum mechanics, which is like the rule book for the smallest stuff in the universe to try and understand the biggest stuff. It's like using the universe to explain itself.
Yeah. It's kind of poetic when you think about it like that. And we're using these mind-blowingly complex machines, these quantum computers, to simulate the universe's tiniest building blocks. It's like we're holding up a mirror to the universe and people are like, come on, spill the tea. What's the secret?
And the secrets we uncover, the answers we find, they could change everything, right? Like, it just goes to show how much is still out there waiting to be discovered.
Totally. This research. It's a huge step forward, but honestly, it's just the beginning. As quantum computers get even more powerful, who knows what we'll find. It's exciting.
That's what gets me fired up about all this. We're not just tweaking stuff we already know. We're like explorers charting a whole new world. Every new simulation, every experiment, it could rewrite the textbooks.
Absolutely. And, it's not just about where we end up. It's about the journey, too, right?
Yeah.
Every step takes us deeper into the quantum world. That's what's so cool.
Totally agree. And speaking of journeys, we've reached the end of ours for today. But before we go, we always like to leave you with something to ponder, something to spark your curiosity.
Always got to leave them wanting more. What do you have ours today?
Well, we've seen how this Hamiltonian truncation lets us simulate these crazy complex systems, even with the kind of limited quantum computers we have now. So just imagine what we could do when those computers get even more powerful. Could this be the key to figuring out some of the universe's biggest mysteries?
Oh, man, the big ones. The nature of dark matter, what happens inside a black hole. Now, those are some deep dives I'd sign up for.
Right. The possibilities are endless. So keep those brains buzzing, keep asking those big questions, and keep diving deep into the quantum world. Until next time.